Okay, hello everyone. Today we're going to continue our talk about performance measures. So, in performance measures, and again, this is for binary classifiers. Okay, so last time we talked about the confusion matrix, and hopefully everyone was able to grasp what that was, because we're going to need it for today's lecture. In particular, we're going to look at what's called the ROC curve. Yeah. Okay, so what this is, so the receiver operating characteristics curve, right? So receiver operating characteristic curve. This is kind of clearly the ROC curve. Is a common tool used to compare binary classifiers. Okay. So I'm going to preface before I write anything else down that the way that I'm defining the ROC curve is not the same as you might see in even some textbooks or YouTube videos. I'm kind of doing it in a way that's specific to the functions in scikit-learn. Okay, so I'm just doing it specific to that package, but there's different ways to define this. So just keep that in mind before I write this down. Okay, so the way that I'm going to define it is I'm going to say the ROC curve plots the true positive rate also known as recall against the false positive rate. Okay. So the false positive rate is PR, true positive rate, PR. So here, the false positive rate, well, I guess I don't need to write this out, I can just write down the formulas for it. So it's the recall, which is equal to the true positive rate, is equal to the number of true positives divided by the true positives plus the false negatives. And the false positive rate is equal to the number of false positives over the number of false positives plus the true negatives. Okay. So these two formulas are what we're going to use to create our ROC curve. Okay. So maybe I'll write them down over here because I'm going to have to erase all this in a moment. So positive rate. False positive rate. Okay. So I think the best way to illustrate this is with an example. Okay, so suppose that we're training a logistic regression curve to fit maybe some features that imply either a patient has COVID or does not have COVID. I'm kind of reminded of this because COVID is everywhere right now, and I get tested every week. And I think it's kind of relevant. So let's just use that as an example. So suppose we have our confusion matrix, and it looks something like this. So we have like COVID negative, COVID positive, and then COVID negative, COVID positive, let me give myself more room here. This is a little bit better. COVID positive here. And here, so along the rows, as you recall from last time, we have the actual class of the data in question. And then along the columns, we have the predicted class. Okay. All right, so and just recall that here we have true negatives, here we have the false positives, true positives, and then false negatives here. Okay, and that's how we fill our confusion matrix. So inside this cell here is the number of true negatives that we predict that are actually true negatives. Here is the number of COVID positives that we predict that should have been COVID negatives. Here is the number of COVID negatives we predict that are COVID positive. And then here, the number of COVID positives that are actually COVID positive, in this case here. Okay. So suppose we have some feature. So I don't know what this could be. When I get tested, I have like nose swabs that are done to me. And then I also have like blood work done every once in a while because I'm a part of like an experimental study with COVID antibodies. They take my blood. So there's some features that they measure when they do this. And then here, if we're going to use a logistic regression curve, we have a probability between 0 and 1 that given some feature that you'll have COVID, right? So this is probability that feature X implies COVID positive or something. Okay. So probability that feature X implies COVID positive. All right. So let me just put down some feature measures here and say maybe like if I use blue as positive and green as negative. So green, 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 like that. And then blue positive. That. And then we've trained some, we've run logistic regression, and we have some curve using the sigmoid function. Looks like that. All right. And then we have, so there, there, for negatives, and we have positives there. So, okay, so when we run logistic regression, as you recall, we get out a probability, a number between 0 and 1, and then we have to decide if what the threshold should be to predict class A or class B, or in this case, COVID positive or COVID negative. So when we did this earlier in the semester, we just picked if we predict a probability greater than 0.5, then we assign it to the positive class. And then if it's less than 0.5, we assign it to the negative class. So one such threshold would be something like, there's like 0.5 right there. So this would be like the threshold equal to 0.5, right? So we input a value and it lands on this side of the threshold. We say that it's COVID positive, and if it ends up on this side of the threshold, we say that it's COVID negative. Okay, so but like thinking to like how contagious COVID is, right? It seems that if we look here, this person was COVID positive, but under this model, we wouldn't have predicted that they were positive, right? And that's bad, right? Because COVID is so contagious, we want to ensure that we predict everyone that has it to be positive. So here we have, so this would be, so let's go ahead and fill in the confusion matrix here, right? So for threshold of 0.5, let's fill it in. So, so how many negatives did we predict that were negative? So we would predict 1, 2, 3 there, right? So we predict 3 that are indeed negative in this case. So how many did we predict to be positive that were negative? We predicted 1, so there's 1 false positive. And then how many false negatives? So we predict this one to be negative, but it is indeed positive. And then for the true positives, we predict 3 that are indeed positive. So there's the confusion matrix for that threshold there. All right, so I'm going to go ahead and write that down. So, true negative equals 3, false positive equals to 1, false negative equals to 1, true positive equals to 3. And this is for a threshold, say, of 0.5. Okay, so that's the corresponding confusion matrix for if we chose our threshold to be 0.5 for this logistic curve that we fit to the data. Okay, so that was 0.5. So now let's do this again for a different threshold and see what happens. Okay, so suppose our threshold is something like 0.9. Okay, so then our threshold would be something like, or actually it's like maybe like 0.8. Let's say maybe. So there, right, now let's fill in our confusion matrix. So how many true negatives? So we predict that now it's below the threshold, right? The probability that would be like 0.7 or something. So that would be predicted negative, that negative, that. So in fact, we predict all of them. Every person that didn't have COVID, every person who's COVID negative, we would have predicted that they were COVID negative. But now, if we look at our false positive, let's see. So how many did we predict were positive that happened to be actually negative? Well, these are all the ones that we would have predicted to be positive, and they are positive, so this would be 0. Okay. How many false negatives? Let's look at that. So, how many did we predict to be negative that are indeed positive? Here's that one right there. And how many do we predict to be positive that are indeed positive? 3. All right, so true positives, so we take that. False negatives, there's 1 right there. We predict negative, but it is indeed positive. We predict all of those there. Yeah. Yeah, and the total number should always be the same. So this was a different confusion matrix for a threshold of 0.8. So let's go ahead and write that down. So true negative equals 4, false positive equals 0, false negative equals 1, true positive equals 3. And that was for a threshold of say 0.8. But so I want you to just like pick up on what's going on now. For each choice of a threshold with logistic regression, we're getting a different confusion matrix. We're getting different predictions, right? So let's go ahead and pick maybe like, let's do this maybe one more time and say, this is 0.1. Maybe I need to do it a little bit lower than that. 0.1 there, and it just happens to cut right below that point there. All right. So let's look at what happens here. So now if we look at our true negatives, how many did we predict to be negative that were indeed negative? 2, those 2 right there. How many did we predict to be positive that were positive? 1, 2, 3, 4. So notice now with that threshold there, we were being really safe. Yes, we're going to get some we're going to get some false negatives, as you'll see, but we definitely got all the false positives, right? Oh no, wait a minute. I was jumping ahead. Let me make sure real fast. So we predict positive. It is indeed negative. So 1, 2. What I was just saying is gonna go here. So false negatives, 0. Right? We don't predict anything that's, so we predict negative, and none of them, yeah, so this would be 0. But now if we look at our true positives, we predict that, and that one, just below that. So now we get all of them. So we were being overly cautious. We were like, if there is even a 0.1 chance that person is going to have be COVID positive for this data set, we're going to say that they are. So, so this would be that we fill in our confusion matrix here. So true negatives, 2 false positives, 2 false negatives, 0 true positives, 4. So notice that we're having like a bit of a trade-off. Like even though we're getting all the positive ones, right? We are predicting correctly the true positives. We're also getting false positives. Okay. Now in a perfect world, that would be 0 and that would be 0, and then we have a perfect prediction. But there's in many instances there's going to be these outliers where they're kind of extremes, and you have to, based off of your model, decide what your threshold is going to be by playing with it and experimenting with it. Okay, so now we can start to build a ROC curve. And the way that we're going to do this is as follows. So here we're going to have our false positive rate, okay, versus a true positive rate. Okay, so let's go ahead and do these. So, and we're going to do that for each of the values of the threshold that are possible. Okay. Now, notice there's infinitely many places to pick a threshold. So it is going to be a smooth curve that we're going to plot. But because we're only going to want to do this like a finite number of times, that's what we can do, it's going to be kind of choppy, right? But when we plot this in Python, it's going to be a smooth curve. So, okay, so false positive rates for theta equals to 1. So false positive rates. So number of false positives over false positives plus true negatives equals 2/4 equals 1/2. So this is for theta equals to 0.1. And then true positive rate is going to be 2 over 2 plus false negative 0, 1. So false positive rate is 1/2, true positive rate is 1. 2 plus 2 plus 0. Yeah. So that point in this plane will be like, so here's like a half, and then up here. All right, so that was for that choice of that threshold. Okay, so next let's do that for theta is equal to 0.8. So theta is equal to 0.8, the false positive rate is going to be 0, because the number of false positives will be 0, right? And then the true positive rate is going to be positive, which is 3 over 3 plus 1. False negatives 1, 3 plus 1, so be 3/4. So if we plot that point, so that's like a quarter, three-fourths, so 0, 3/4. Okay. All right, so let's do one more point. Let's do the threshold of 0.5. Okay. So then false positive rate is going to be, so false positive 1 over 1 plus 3, so 4. Okay. And then the true positive rate is going to be equal to 3 over 3 plus 1 or 3/4. So 1/4, comma 3/4. So 1/4, comma 3/4. Okay. And if we plot this curve, it's going to look something like this. All right. It's never going to go above 1, and you're not going to get it past 1. So that curve looks like this. Now, depending on your application, this tells you a lot, right? So here you have 0 false positives at that threshold, right? And your true positive rate is at 3/4. Here you have you get all of the true positives, right? But then you also have you also report some false positives. So in the case of the COVID example, you'd want to choose a threshold at this bend here. But depending on your application, your bends are going to determine what thresholds you typically are going to want. Okay. Now, notice now that so you can compare, so note, you can compare classifiers by comparing or not by comparing, maybe by measuring. By measuring the area under the curve under the ROC curve. Okay, and this is called the area you see, area under the curve. So a perfect classifier, an absolutely perfect classifier, would have a true positive rate of 1 and a false positive rate of 0 everywhere for any threshold that you pick, and the area would be 1, right? So for any threshold you pick, you're always going to have a true positive rate of 1, right? And your false positive rate is not going to change that. Okay. But so suppose like I'll call this like blue is this area, so right here. So it's for this curve, right? And that was for, so that, suppose that this was for logistic regression for this problem. So blue is logistic regression. Okay. But then suppose we had another model, like, as we'll see, maybe something like a decision tree or a random forest, which we haven't learned what those are yet, but we will. They have a curve like this. So then, so the ROC curve for the random forest looked like that, and its area was that. So green is like maybe a random forest classifier. So since the area of the random forest ROC curve was greater than the area of the logistic regression curve, then we would say, oh, this, for this given problem, this random forest, I don't know if you can read that because the screen is too bright. Green is a random forest. We'd say that since that area is more, that for this problem, the random forest was a better classifier. Yeah. Okay, so that I think will be it for today's lecture. I'm going to post this to YouTube, and then I'm also going to post a video where I show you how to compare ROC curves using Python for a given problem. So that'll be it for now, and I'll try to get that programming video up using Python later today or tomorrow. Any questions? And if you're curious as to what chapter I'm in the textbook I'm using, I am in chapter 3, the section on performance measures, and this textbook. Okay, so chapter 3, pages 95 through 100, really. Okay. All right. Okay, so everyone stay safe. I'll talk to you soon.
Thank you.
Email me if you have any questions.